I think this is 2.8 to 2.12. I think 2.12. You'll see the title. Uh, you have here drag and drop to complete the diagram describing electrostatic precipitator. This is a very bad diagram, but I'll show you how it actually looks over here. You have two neutral plates, and you have dust that comes down. You have a positive grid over here. So what happens is the dust hits the grid, which positively charges the dust, which will make the dust repel from the grid and hit and stick onto the metal plates. Okay. So this is all explained in the notes. You can go up and read here. And it was here. It was oof, 1 week 6. It was, yeah, from here. Where 1 week 5. It was in the notes for 2.1 till 2.9. When I send the text, you'll see it over here. The electrostatic precipitator at the end over here. Yeah, electrostatic precipitator. They didn't ask about the lightning conductor here in the quiz. I don't know why. Uh, Neither did they ask about the paint gun or the fingerprints. Really quickly, uh, how we can apply electrostatics in real life by using a paint gun to spread paint evenly on surface. A highly efficient technology using electrostatics has been invented. Electrostatic rain gun. Oh, so this here, there's a lot of yap, but yeah, to sum it up, okay, what happens is at the atomizer tips over here, there's an ionizing electrode. Okay, so basically it just makes all of these paint that come out, makes them negatively charged. Oh, they spray them on a positive wall. Okay, the negative paint will attract to the positive wall, and it forms a thin coat. Okay, this the negative charge then leaks through the ground, returns to the power supply. La 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 la. Yap yap yap. Okay, this produces an even distribution of paint, and it also saves paint by reducing overspraying. Okay, it's very efficient, but it's not suitable for all. Okay, la 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 la. Okay, Anna, it's because I don't remember mentioning the paint gun in my notes. Yeah, I didn't. But fingerprint, I did. Fingerprint is, and to sum it up, you have positively charged metal plate that's charged. Oh, there's a specimen, يعني أنت where you put your finger. Okay. When you press it, the powder will go up. It goes to the negative plate, becomes negatively charged, it sticks. يعني I explained it here. You connect the power supply to two plates. One plate connected is to the positive side, and the other is connected to the negative side. You apply powder on the positively charged plate, making the powder positive, so هون بتحط powder. The other plate is connected to the negative side, which with negative. When the specimen is pressed, so into when you put your finger here, the positive powder it goes up to the negative specimen, where the powder attracts to the tip of the finger, and it will thus become negatively charged. Then the powder will stay there. This is يعني, they never asked about these in any quiz or anything, but I'm just saying that in case they come. Question 2. Okay, here workers manufacturing computer chips must take care not to become charged, as the electric discharge may destroy expensive components they are working on. So, the benches the chip manufacturers should sit on should be made of metal. Why? Okay, let's see. The whole point of them sitting on metal is that so the workers don't become charged. Let's see here. Enter if you sit on an insulator. Okay, this is you over here. Okay, enter you're working. Imagine the Chinese factories where they're like all they're making phones or yeah. Okay, this is your chair. Okay, you can put like another one here. Okay, so انت you're working عم تشتغل انا احط له smiley face على الكمبيوتر هون. Let's put it like this. عندك الكيبورد. Okay, I don't know why I'm enjoying this بس okay, عندك الكيبورد هون و you're typing, I don't know, you're working. Okay, well, they have to take care not to be charged. If you're gonna يعني انت you're gonna start taking the charge because since you're working with electronics, you might get charged, right? You're gonna start getting charged. If you're sitting on an insulator, the insulator won't allow these charges to move, so the charges will build up on you, right? So that's why we're gonna sit on a metal, because metal is a conductor, and thus, if you're sitting on a conductor, the charges that will build up on you will thus flow into the metal, thus being earthed into the ground after it flows through the chair, right? So that way, such branches will ensure earthing of the chip manufacturer's bodies. This will ensure that the charges don't build up on you, or the charges will leak, so you don't become electrocuted. Okay. Well, you can see, by the way, if you look up phone factories in China, you can see this. Okay, here, drag and drop the correct direction of the electric field between the plates of the complete diagram. Akid, here you have positive, here you have negative. Please don't make, since in the book they put positive on the left and negative on the right. So please don't make the mistake of putting this. Don't put this. It's positive on the right and negative on the left. It always goes from positive to negative. That's why we choose this one, okay? Consider 2 points A and B located between the two plates. If the electric field at point A is EA and the field at B is point EB, how do their magnitudes compare? How far are they from their plates? The same. I think, huh? Uh, I think I think this is why, by the way. Yani, because you didn't mention it in the book. But yani, I think it's because شو اسمه, they're both at equal distance from their plates. Well, are they? Yeah. So that means their electric field is equal. Then they said if the force on charge FA, okay, yeah. They're saying if the force on A is FA, with force on B is FB, how do the forces compare? FA is equal to FB. If you remember, by the way, here, Coulomb's law over somewhere here. When you have two particles, the force on the first one is always equal to the force on the second one, okay? And that in total is equal to this equation. So anytime you have two forces between two particles, okay, they're equal to each other, okay? That's how it works. It's a law because they're both between two electric plates. Let's say you had one, if let's say B was here. Which one would be greater, EA or EB? Akid EA in this case would be greater than EB, right? Remember that the electric field is always equal to the force divided by the charge. Here, and both here, they're both flowing through the electric field. So the same force among the same charge is that tells you في electric field that's equal. هلا for what is true about an electric field? It has a magnitude and a direction, of course. And the magnitude of the electric field is force divided by charge, of course. It's scalar, of course, no. If it has a direction and it's a vector. It's best described using charged spheres, no. The magnitude is the work per charge, no. Right? If you want to go back and see electric field, ارجع هون ل 2.10 شي مكان هون. Over here, an electric field is vector quantity. It has both magnitude and direction. It's the force per unit charge. If a charge Q node experiences a force F, then E is F over Q node. A useful way is with electrical lines of force, not with spheres. Okay? If the lines are further apart, the field is weaker. A field line points away from a positive charge. Okay, la 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 la. Okay, and I think I described this in my 2.10 notes video. That I described all of them and how they look. Okay, for this one specifically, they may ask you this as it goes further away, it starts to curve a bit. Okay, but they may ask it. They may ask it, but I don't know. Honestly, well, I don't know. But usually it's just straight. Okay, but as you go further outwards, it begins to become slightly curved. Okay, just in case you see it. 5. Electrons of charge 20 microcoulomb are transferred from metal A to B via conducting rod. The charge is transferred in 5 milliseconds. What is the direction of current? They said that the electrons are going from A to B. And we know electrons move from negative to positive, right? Now we want current. The current always flows from positive to negative. Okay? In this case, they're saying us A to B is electrons. Yani A is the negative or B is the positive. Now we want the current, which goes from positive to negative, so B to A. Okay? In other words, the motion of current is always opposite to the motion of electrons. Okay? That's how you can know it. Then what is the current in the rod? You know, current I is equal to Q divided by the T. And now we have the charge in coulomb is 20 microcoulomb. To convert it from microcoulomb to normal coulomb, and you have to multiply by 10 to the power negative 6 because micro, this symbol is micro, and you have to change it times 10 to the power negative 6. So 20 times 10 to the power of negative 6 وهن I think they're asking us to keep it in milli, but we can change it later. Let's forget about this later. Forget about this. Let's keep the time. The time is in millisecond. نحنا we want to change it. When applying the formula, it has to be in second, not millisecond. And to go from milli to normal, you multiply by negative 10 to the power of negative 3 or divide by 1,000, right? So you put 5 times 10 to the power of negative 3. When you do this, I'm pretty sure you get 0.004. It's fraction simple. 20 times 10 to the power of negative 6. وتحت عندك 5 times 10 to the power of لا negative okay. Hey, you get 4 times 10 to the power of negative 3 ampere, right? بس نحن بدنا إياه milli ampere. To convert from normal ampere to milli ampere ما بتعمل times 10 to the power of negative 3 بالعكس, right? You're now going smaller. When you go smaller, you multiply, right? Because there's going to be more of it when you're going small. From ampere to milliampere. Milliampere is smaller than ampere. If you want to become something, if you want to put it in terms of something small, you have to multiply, أكيد, right? Not, يعني it's going to be times 10 to the power of 3, not times 10 to the power of negative 3. بيطلع لك 4 milliampere. And I just want to see if you keep this in milli, would you get the same answer? 20 times 10 to the power of negative 6 divided by 5. Okay, yeah, you get the wrong answer. So you have to convert this into normal second. و... ah, ah, okay, no, that's something else. Okay, yeah, just make sure to convert to seconds. At the end, change it around, play with it however you want. Which of the following can be referred to as an electric current? Electric current can be the flow of positive charges as well as the flow of negative charges. And it is very important that you say it is the flow of charge in an orderly manner. In an orderly manner. That's the way they define it in the book. Somewhere here. I think it was. Give me a sec. It was here somewhere. I think after the electric. Yeah. Hey, it's somewhere here. Hold up. Yeah, over here. Electric current. Okay. According to the theoretical model, electric current. Oh my god. Oh my god. Electric current is the flow of negatively charged particles or positively charged particles or both in an ordered manner. Okay, that's what matters. To obtain an electric current, and here they also redefined it. An electric current can be defined as. I swear to God. Can be defined as a flow of electric charge. Okay. All the experiments I did them in my notes. يعني this is just to show there's a few conclusions at the end of this. An electric current is the flow of negatively charged particles or positively charged particles or both. However, according to the accepted model, in metals, only free electrons move. Okay? And then here, I think they said something about okay. Okay. Yeah, okay, this is just yap here. حتى here in my notes, the movement of electric current involves the ordered movement of electric charge. In metals, the electric charge carriers are the conduction electrons that are free. Okay. In metals, it's only the electrons. Electric current can be defined as the flow of electric charge. By convention, we know it's always from positive to negative. This is opposite to the flow of electrons. Okay, this is here. It's just take experiments. You have the galvanometer to detect very small electric current. The galvanometer. Okay, I'm gonna be repeating myself if I go through these. I 100%. I explained this in my notes video. 100%. Okay. So it's flow of negative and positive. It's obviously not neutral. A random motion is not random. It's not random. It's ordered. Okay. 7. In a circuit, 3 coulombs of charge flow in. Okay. Current I is equal if you have Q over T. We have the charge in coulombs, which is the Q, and the time. Divide 3 by 0.6. You get 5. Okay. 8. I'm sorry. 11. Okay. Two electric plates. Okay, this is a nice question. I liked it. Two electric plates are initially neutral. Okay. 10 to the power of 20 electrons are transferred from plate 1 to the other one by doing 32 joules of work. So عندنا W, or the energy, equals 32. Use E is equal to this. Okay. The charge on the plate lacking electrons. نحن عندنا number of electrons وعندنا ال E. How do we find Q? Remember, Q is equal to N times E. Okay. It has to be positive, so yeah. Here, أنا to solve, like I told you, I don't like solving with the negative. Okay, I keep the negative at the side. وأنا I use it as positive, and then at the end, I see, you know, whether I am talking about positive or negative. That's I make my answer positive or negative. I'll show you both ways. I'll show you the way they want us to solve. Use E as negative. You're gonna get the number of electrons, which is 10 to the power of 20, 1 times 10 to the power of 20. E is negative 1.6 times 10 to the power of negative 19. وبيطلع لك charge, which you'll see. Why am I no يا اخي بديش Spotify بديش. Do you want to cancel? No خلاص. لا close. Hold up. Okay. 1 times 10 to the power of 20, okay, times negative 1.6 times 10 to the power of negative 19. You get negative 16. So the charge is Q is negative 16. But here, if you put negative 16, you're going to get it wrong. Okay. Now we have a positive plate. If you look at the question, you have one plate and another plate, right? They were both initially neutral. One gained electrons, right? Let's call plate A, plate B. Okay. The charge, let's say they moved from A to B. So A would be the one lacking electrons. So would it make sense to give it a negative charge? أكيد no. We're going to make it positive. The charge on the plate with a surplus or extra electrons, the one that gained electrons, say plate B, they both have the same charge but just opposite signs, right? This one would be positive, and since this one gained the electrons, it would actually be now negative. So it would be negative 16 coulomb. Then they say, what's the potential difference? Okay, potential difference W. شو W قصدي V. Potential difference V is equal to W over Q, or otherwise known as W equals QV. But just take Q here, you'll get W as over Q equals V. So you're gonna get the work is 32, and the charge is how much? 16, right? So 2. Please use a positive amount for the charge. And you're gonna get 2.0 volt. Okay, if you want, keep it as 2. I think I kept it as 2. Yes, it's fine. The negative answer is also correct. Okay, honestly, I use the positive answer. Okay. Why we need part A and B is because we need to find the charge Q so that we can solve part C. Okay, please don't use this charge. This is the charge of an electron, guys. Don't use that as your answer. Okay, if you used my way as keeping it positive, like for part A, if you used my way, keep it positive, you'd get 16. And what I did is I said, oh, 16. Okay, let me see. They want the one lacking electrons, so I'm going to keep it as 16 because it's positive. And then they want the one, oh, it has extra electrons. I made it negative 16 because it actually has a surplus of electrons. Both are correct, guys, whatever you want. In order to move 2.5 coulomb of charge against the potential difference 24, how much energy? W equals Q times V. Well, charge is 2.5, the voltage is 24, multiply, and you get 16, okay? 10. Current is 4, potential difference is 12. What's the power? P equals IV. Okay, current is 4, power is 12, 4 times 12, 48. What's the energy drawn in 5 minutes? Energy is equal, or work is equal to power times time. In other words, by the way, P is equal to work or energy divided by time. That's why if you rearrange the equation, you're going to get work is equal to power times time. That's why work and energy, they're the same thing, okay? So you can just like, and it's the same thing. Work is in joules, energy is in joules, is the same thing. Okay, so the power we found in part A, 48, with the time given in the question 5 minutes. Please do not use 5, use it as 300 seconds. Walid, why يا أخي? Man, the SI unit of time is in seconds, so you must convert to seconds whenever you want to put time in any equation. But to convert from 5 minutes to seconds, you multiply by 60. 5 times 60 is 300, so 300 on. وهنا they want it in kilojoule. In kilojoules to one decimal place, 48 times 300. In kilojoules, you divide by 1000, you get 14.4. Okay. The amount of charge that flows through the circuit in 1 minute, up to the nearest integer. Charge Q is equal to I, the current given in the question, where they gave you time, so Q equals IT. This equation. Current is 4, time is 1 minute, in seconds that's 60, so it's 240 coulomb. Okay. The last question came in AMS, by the way. in a circuit 2 amperes, so they gave you I, they gave you volt, they gave you time. Okay, they want the power. Remember, P equals IV. Or in this case, 2 times 12 is obviously 24. And they want the energy. Uh, you get 24. 2 times 12. Okay, then the energy release. Remember, power is equal to work or energy divided by time. So the work or energy is equal to power times time. So the work is equal to the power, which is 24 from part A, times the time, which is 300 seconds. It has to be in seconds, and you get 7,200. But they want it in kilojoules, so you divide by 1000 and it will become 7.2. Okay, easy. هيك نكون خلصنا. Thank you so much for watching. Good luck.